Hello, everyone. Good morning. Good morning. Good morning, everyone. A couple of minutes and we will get started. For now, I will share the whiteboard. Yes, okay. Morning. The whiteboard. And so, yeah, let's get started, folks. Let's get started from the questions, probably. Any questions from the last week or in general about everything? Okay. So if someone joined first time, just please let me know. For now, I see that all familiar faces joined us. So because I'm going to share some organization questions regarding the course. So today we are on the week 11, and next week will be the last one, which is conclude 12 weeks of summer LeetCode Bootcamp. Thanks everyone who makes it till the 11th week. So and hopefully till the 12 weeks. On next week we will cover the second part of graph. Today we will start from basic and introduction to the graphs, and we will cover DFS. And next week we will cover BFS and probably yeah. For medium week, so it's actually I was about to post it. Who is eligible for the certificate? Because it's already 2 weeks more. We are in the middle of hard week, so it would be great if you can finish at least this weekend. And then also this weekend I will post it names. If there will be someone missing, just please let us know, and we will issue certificate for midweek.
Lilia, were you saying the last day for completing the medium level challenge is still not crossed, right?
Try to finish over the weekend.
Okay. When you say medium level, which was the last which was the last topic we covered? Because I don't know when we started hard.
Yeah, I think it was 3 introduction session.
Okay. Okay. Yeah. Thank you.
Nope. Okay. There are someone who joined first time. If you have any questions, just unmute yourself and ask. If there is no question from you, so it's okay. Any questions, folks? Okay, cool. Let's get started then. By the way, I don't see that many finished last week. Just we'll check. Yeah, don't hesitate to ask any questions. I will try to help on the Slack if there is something is missing, because there is some people, many people sign up, but not everyone is finished. Okay, let's get started then from graphs. This is quite a popular topic during the interview. Maybe there is probably not during the phone screen, but definitely during the on-site. There is usually at least one question. And I start recording, folks. Okay, recording. So, do you see my screen? Okay, cool. And you have whiteboard, right? Everyone is having it. Okay. So, introduction to the graph. We covered tree so far, and we covered try. Graph, it is a data structure composed of nodes connected by edges. So basically, tree is actually a graph, but with some restrictions. I posted what is the difference at the end, but keep in mind that it is actually tree. It is a graph. Tries, it's also a graph, but some special type. So for those who was a part of tree and try, the material should be kind of not complex, I would say. So graph is used to model relationship where edges define the relationship. As usual, graph node is represented this way. We cover how tree node is represented, try node. This is the representation of graph node. It contain neighbors. So for tree, we cover that it is just up to 2 childs, left and right. For try, it was also neighbors here. Which was belong to the node. So the same for graph. Terminology. So adjacent node, neighbor, two nodes are adjacent if there is an edge connecting. So we have this node, and he has adjacent neighbors 3, 2, and 1. So degree connected to them. Degree, the number of edges connected to the node. So for example, this node has a degree of 3 because there is 3 nodes is connected. It will be important, this terminologies next session when we will cover topological sorted, because at this time we are taking a degree and we are working with degree in order to perform topological sort. Path is a sequence of nodes connected by the edges. So it's similar to what we covered during the tree introduction session. Okay, attributes. Direct vs indirect. In an indirect graph, edges have a direction associated with them. So basically, tree was directed graph, and I emphasize it during the. Just 1 second. We'll send link again. So basically, tree was directed graph. Means we knew that 3 is connected with 0, but 0 is not connected the opposite way with 3. But when it comes to graph, it could be undirected graph. Means 0 is connected with 3 and 3 is connected with 0. This is clear? Okay, cool. This is important because quite frequently there is a task you should understand whether it is directed graph or undirected graph. Weight and unweighted graph. So this is weighted graph. This is unweighted graph. The difference is that on the edge you have weight. This is related to more advanced algorithms related to graph, where you need to take into account weight in order to find the path. So for example, and it is also the same algorithm regarding the weight is usually used for the routing system. When you need to route the traffic, so basically you're taking into account weights and you build the best path how you want to route the traffic. I'm not sure if we will, because I haven't yet prepared the material for the next week. Probably we won't cover because it's quite advanced topic related to graph. But if we won't cover it next session, we will definitely cover in autumn. So yeah, this is the directed graph. Next, there is cycling and acycling graph. A cycling graph contains at least one cycle, which is the path that start and end at the same day, at the same node. So this is the cycle in the graph. Tree on the other side can't have cycle, but graph can. So the difference between graph and tree, that tree should not be cyclic. It is contain n-1 edges compared to graph. And what was the third one? It is and it is directed graph. So three things which is distinguish tree from graph. Okay, this is clear what I just described. Okay, we will cover task on finding cycling in the graph next time. Okay, representation. In some problem, you might not be given the graph directly. In this situation, it's usually necessary to create your own representation of graph. This time, we won't create graphs, but next time, while we will doing topological sort, I believe at this point you would need to build a graph. So the two most common representation, it is adjacent list and adjacent matrix. Adjacent list, I would say, the most popular representation of the graph. For me, when I was first time working with graph, this was probably one of the toughest things which I needed to understand how to build graph actually. So adjacent list looks this way. The neighbors of each node are sorted as a list. Adjacent list can be implemented using a hash map, and it's usually implemented as a hash map, where the key represents the node, and it is corresponding value represent the list of nodes neighbors. Adjacent matrix, the graph is represented as a 2D matrix, where matrix indicates an edge between nodes A and G. So this is the representation of undirected graph. You can see. So we are establishing and how to build actually this representation. When it comes to undirected graph, first you initialize a hash map, and then you're trying to build. So first you're putting node, you are creating the list empty. It could be different. It depends on syntaxes in your own language. So I provided here Java. Probably at some languages, you don't really need to create the empty one, and you can directly to do something like. But in Java, it is first, you need to check if you already have neighbors. If you don't have neighbors associated with this node, you're creating the empty list. Then you're taking this node and you're adding a neighbor which is associated with this node. But as graph is not a direct one, you need to build the same way association with V node and adding U. Is it clear what we are doing here? Okay, cool. So in case if it will be directed graph, that's why it's important to understand from this description, you are not going to include this line of code and this line of code. because it is directed one. When it comes to building a JSON matrix, you're doing this way. So you're creating a matrix. This the numbers of nodes. You're putting the size of array because you need to initialize it. And if there is actually a relationship between the nodes, you're putting a value. So this is how you indicate if there is an actual relationship between these two nodes, if there is age exists. The same way, I mean, if it's a directed graph or undirected, if it's undirected graph, you need to build the same relationship the opposite way. Is it clear?
Okay, sorry, Lilia, what's an adjacent matrix? Maybe I didn't catch that.
Say again?
I'm trying to ask what an adjacent matrix is.
Adjacent matrix is this one matrix.
Okay. Yeah. Okay.
Yeah, so basically it's indicate that you have relationship between 0 node and 1 node. You're putting 1, but because it is undirected graph, means between 0 node and 1, you also have relationship. So it is indicated 1. And if there is no relationship, it will remain 0.
Okay.
So yeah, it is just matrix, 2D matrix. And this is the JSON list when you have a key and it is associated with list of nodes. Okay, traverse. It will be the same like for tree. It is supported DFS and BFS. They're absolutely the same like we did for tree. DFS typically implemented as recursively, but with stack as well. So this is the snip code, how we are performing DFS on the graph. This one, we will cover this a little bit later in one of the tasks, in two actually, I believe. Yeah. So just will spotlight. So visited, it means because the graph could be undirected, and you can visit and you can stack in the cycling. But you need to track in some tasks. You need to track most of the tasks. You need to actually track whether the node has been already visited or not, and it's also some performance optimization. Some tasks you can implement without visiting, without tracking which node you have so far visited, but some. This anyway, it's usually better to implement because this how you will improve the performance. You will see in depth in next task. So usually you can visit it. It is usually either hash set or I believe there is hash set or there is another approach. I will show two approaches how we track the visited nodes. So you process node, then you're taking all neighbors from the node. There is some logic. It is not a recursive function here, as you see. You just process node, whatever logic you have. Then you're taking all the neighbors of the node. You're checking if it wasn't visit. If it wasn't, you're calling the recursion function. What does it mean? If you will look at this, so basically this graph, you're starting from this node, you process something here, then you're taking all the neighbors. At this point, when you're performing DFS, you already have your representation of the graph. It's either a JSON list or matrix. We will cover both today. So means, and it will look like this. The node. Do you remember it is neighbors? So basically, you have node here. You're taking node, you process something. Then from this node, you're taking all the neighbors in for and going and executing the phase on each of these neighbors node. So you're calling the phase here, here, and here. And is it a recursion function? Means you will go also the phase here. And it will backtracking back and will give you some logic. So it's absolutely the same like we did the phase with recursion and we stack for 3. BFS will be the same. Again, like with 3, we again tracking visited nodes for BFS as well. We're using queue. We're popping out queue. We process nodes. The same things. Once we process node, we're taking all the neighbors. All these neighbors will be as a part of queue. We will putting them in the queue, and we go again. It's also the same. BFS is a level process of the node, and DFS it is going in deep and then backtracking. So means when we're going with DFS, you are processing this node, then it will be backtrack and will return result here. With DFS, it will be you starting from this node, and you will process this level of nodes first, and then you only will process this one. So depends on the task which will be asked. BFS won't be covered here. You are choosing either using DFS or BFS. Any questions here? Okay, just to sum up, what is important? Important to understand types of graphs, directed and undirected. Weighted and unweighted, you can keep aside. I barely see that anyone is asking during the interview questions on the weighted and unweighted. On the other hand, cycling and acycling graphs is quite popular LeetCode question. So direct, indirect, cycling and acycling. Important terminologies here is degree. Path we learn the same with tree, so it's basically the same with graph. Representation of graph is very important. Adjacent list or adjacent matrix. Usually, a very popular one is adjacent list. So how to build graphs? You need to understand it. You won't practice this week how to build, but next week I will include task where you need to build a graph. So the same way we are traversing with DFS or BFS. This is the pattern template for code snip with DFS and BFS. DFS it is the recursive implementation, but again, you can use stack as well. So that's it. If everything is clear on this, I'm going to cover first task. Okay. So problem statement. Given a reference to a node within undirected graph, create a deep copy of the graph. Oops. The copied graph must be completely independent of the original one. This means you need to make new nodes for the copied graph instead of reusing any nodes from the original graph. So in a nutshell, you're given as an input original graph. What you need to create? You need to create just clone of this graph and return it. Is it clear? Okay. The strategy is traverse the original graph and create the deep copy during the traversal, effectively cloning each node while traversing. Any traverse method will sufficient for this strategy. Means BFS and DFS will work in this task. You can solve both way, but DFS is more cleaner and more shorter. And usually, but you, if you will struggling with using the face, I mean, from the recursion point, there is always the way to solve it with BFS. So the idea is just to traverse graph in any way and make copy on the during the traversing. So let's look at the face implementation. When the face is called on the input node, the goal is to create a deep copy of that node and all its neighbors. So yeah, this is a small, we will start from 0 node. We will call the face. We will create right away clone node right away, not waiting. Ensure this clone node is connected to the clone of, this is will be kind of a bit tricky part, how to ensure that once we've created the clone node, that this clone node actually will be connected not to the original nodes, but actually to the cloned nodes. So to a clone of it's mirroring the original nodes. Ensuring this cloned node is connected to a clone of all its neighbors, mirroring the original nodes of neighbors. Okay. So in that, how initial code will looks like. We're starting from 0 node. We right away creating cloned copy of this node. This new graph node will be provided as a part of data structure. So we have already graph and it will be provided. We will create, let me actually show you this. So we have already a representation of node here. Here will be graph which is already built. As an input, you will have node. I need to double check one thing. Map Q clone put start. Okay. I think I need to fix this one. Just I will open LeetCode and will explain you how it will look like. So that's you have class node and you have some constructors. That's how you will create it. Yeah, now I understand. It should work as well. So yeah, we're providing there will be the constructor. Everything what you need, you just need to create a new new node, which will be called clone node. So this is you're starting from this node. You're creating first when you're entering the devise function. You will start first things as on this picture. You will create cloned node. Then from the existing node, the original one from 0, you will take all the neighbors, which is original one, will be 1 and 2 here. You will go to for cycle here, and on each node 1 and 2, you will call the devise function here. Meaning, you will go and proceed in the recursive way until you will hit hit that there is no actual neighbors. And for example, this node is all alone here, and you will come back with the cloned node over here. Means, so for example, once we will hit, we will call the devise function from here first. We will create 0. Then we call the devise function from 2. We will create clone node 2. Then we call the devise function of neighbors for 3 here, because 2 still have neighbors. And when we will go with 3, you will create here a clone node of 3, but it doesn't have any neighbors. It will return just 3. So basically, 3 will return back answer to 2. Here will be a cloned neighbor of 3, of this guy, of 2. You will take, but because of here will be 2 cloned node, you will take this cloned node of 2, and you will add to the neighbors cloned neighbor, which is 3. That's how you are going to solve, and be sure that actually your cloned node is associated only with cloned nodes, but not with original one. This is clear. Otherwise, I can do with some dry run.
Can you please do a dry run?
Yeah, sure. So basically, here will be 0 first. 0 has neighbors 1 and 2. This is understandable from where neighbors has come from.
From the adjacency list, right?
Yes. Yeah, correct. Here, first you will call the phase. So for example, 1, depends on the order, they will come. 2. Next, you will come here 1, because you're calling the recursion function. As 1, so for example, I will go with 2 and 3 because there is some tweak with 1. As neighbors of 1 is actually 0 and 2. Let's just focus on this path. Then I will explain how we are going to solve, because we are from this graph you can see that once we will start from 0, we will visit actually 1 and 2, and once we will call devise on 1, we will visit 2 and 0. I will explain just here how we are going to handle it. For now, just focus on this path. So here we're calling devise on 2, and now 2 has 0, 1, and 3. Let's focus just on 3. Then I will show how we will handle 0 and 1. So let's assume now we are calling function here, devise. Oops. We are calling here devise on 3, meaning here we will come with 3. 3 doesn't have any neighbors. We won't go to this cycle. This cycle will be omitted for us. On this way, we will return 3. Here will be returned our clone node 3. This is understandable, Moina?
Not exactly, sorry.
Yeah, see, we have two, right? We have a list of neighbors 0, 1, and 3. Keep aside this 0 and 1. So, for example, we go to 3 here. We will call 3 neighbor here. It will come. It will call the first function with 3 now. Right away, we will create clone node for 3. This is our cloned node 3. But because of 3 doesn't have neighbors here, we will skip this 4.
Right, that makes sense. Yeah.
And it will just return clone node, which is you created here.
Okay.
Means this defise function will return value, and your cloned neighbor here will be free. You will return. But in this time, when you return, when you go out of defise recursion function for free, you're coming back to this node, which is 2. Means cloned node here is actually 2. Cloned neighbor will be here 3. This is clear how it is happened.
Okay. Yeah.
And cloned node, so this is 2. We will add to the neighbor 3. That's how this recursion function will work. Now the things how do not visit all the nodes which is associated with each other. So it's undirected graph, meaning 3 actually has neighbor and it is 2. So I will explain how. Just 1 second. We'll consider node 2 with neighbors 0, 1, and 3. If 0, 1 have already been cloned, but 3 hasn't. This defise call to 0 and 1 should return the existing clone instead of creating ones. If it's fine, let's consider this example which is I put here. So means we will proceed. We will process second node. Second node has 0, 1, and 3 nodes. 0 and 1 have already been cloned, but 3 hasn't, as we just discussed here. Okay, so instead of cloning, again, 0 and 1 do not duplicate once and adding, because it won't be right. We need to have some tracking mechanism how to track who has been created so far. So we use implementation. Each original node is a key and clone. 1 second. When coming, we must ensure we don't for nodes. Clone instead. Previously created node defines new node. For this, we will have set, which is will track. It's not set. It will be hash map. In order to track, why hash map? Because before I was explaining that for some tasks it's enough just to track with set. So basically, once we will create it, let me probably. So this is the code which is will solve this task. Now let's see what has been what is the difference between this one. So here we're still creating clone node. But once we created clone node, we introduce hash map here. This is how it will look in Java. So you are creating hash map. It is the global variable. It could be as a parameter here, like scene. Whatever works best for you. So you just will carry on. But in this case, we have a hash map, which is seen, and both key is nodes. In this case, this one node is original one, and this one actually the cloned one. What's happened here? So we are creating cloned node, and we are right away fixing that we have already node. and it is cloned node. Next, we are taking from this original node in the face all the neighbors. We are going. We are calling the face function here with node, as we did before. But first check will be if we seen already this node or we don't. And if we see it, so for example, if we will take with two nodes, imagine example, we are processing the second node here. We will check if second node is actually containing here or not. Actually, no. We will start processing two, but two node has neighbors 0, 1, and 3 here. This is clear what I'm on which step I'm trying to explain graph. Okay, cool. So first we'll go 0 here. As we are starting from 0 means we already have this hash map which is containing 0. And we check if you have 0, he's saying yes, I have, and you will just return. Meaning you will return right away here next clone, and you will put it here to your neighbors. That's it. You are not going to call another recursion function because you already processed this node and you already know that you have created a cloned version. This clone version of 0. It will return right away. Next, you will go with one neighbor of 2, and it will be the same because you will process it. You will process and you will just return cloned version here. But this won't happen for 3 node because we haven't seen it's here, and we will create cloned version of 3. We will put it in the scene here. And node 3 actually has neighbor 2, as we saw. We started from 2, we came to 3, right? But 3 at the same time also has a neighbor on 2. This is the tricky part with undirected node, because we should consider both way, here and here. Even though 2 call it 3, okay, we executed the first function. 3 also have neighbor of 2. Meaning here, and it also should include the list of the cloned function. But instead of processing the second node twice time, we again will find it here. We will return 3, and we will come back from the recursion function of 3. And 3 will be as a part of second node right here. So meaning 2 will be first at the list of 3, and 3, and then after processing all the neighbors, will be part of 2. Is it clear, folks? That's how we are assuring. Otherwise, if there won't be this check, we will ending up in processing the same nodes multiple times, and it will be causing the stack overflow because we won't never finish our devise recursion function. Do you remember there should be a base case for any recursion where you actually can go out of the recursion function? Is it clear? Yes.
So, Livia, if we don't have the clone map, it just keeps going through the graph.
Yes, we'll keep going, creating on the neighbors. Yes,
okay.
And we'll never go out of the loop.
Okay.
So yeah. So yeah. Otherwise, it is we have our main function. We are creating the first recursion helper function as we did for 3. We are taking as a parameter node. You can include actually, instead of using global function, here hash map of the scene. But yeah, first you will create a cloned node, then you will check all the neighbors from the original, because you're taking original, and you are just duplicated, creating the cloned version of the main things which is you have to keep in mind, that adding to the neighbors, it should be next cloned version here, and obviously you're returning here clone node, and eventually you will return some node, whatever, there is no restriction on us which node, but you will return actually the cloned node. And from this cloned node, it will make the underneath validation. The same way it will process as a devise or bfs will traverse your graph and will check if actually all the node is a cloned one, and there is no relationship between cloned to original one. Yes.
Hey, good morning, Lilia. I have a question. I feel I'm missing something. On the beat van, we speak about collecting information about nodes we came across already. So when we do it, do we keep a track not only the node itself, like its value, but also its neighbors? Because we could come across a situation in the graph when we have multiple nodes with the same value. How do we make sure that when we do this check, if we came across them already, how do we make sure that this is the node we actually want to check, not some node which we came across, like, I don't know, 310 or whatever number cycles ago?
If I correctly understand your question, one thing, that we are not tracking neighbors, that's what you're asking.
Yeah, and if we are not tracking neighbors, how do we know, like if we have a graph where multiple nodes have the same value, how do we know that we looked at this particular node already?
Because when you will return, so for example, once you have 0, once you process 1, because on the 1 you make a couple of recursion function, right? You at least will go recursively to 2 and 3. And if your node, for example, here, how to say, let me put this example. So for example, if I correctly understood your question, I think I understood. If not, you can then just correct me. So for example, here we will have node, which is, for example, 4. This is our original one, and this one original one. So we will call devise here. Then you will call devise here. You will call devise here. So your question is once 2 will call will like to call devise on 1, we will return right here the cloned version of 1. So your question is how we understand that this one actually is the cloned one already, right? Or it is not correct understanding?
Not exactly, sorry, Lilia, it's me explaining badly things. My question is about, maybe it's like, maybe I misunderstand graphs overall, but like if you look at the original picture with 0, 1, 2, and 3, we have a situation when it's the 3, we have number 1 again.
Number 1 again, yes. So first, when you process 0, you will process 1 and 2, and when you will process 2, you will process again 1 and 0, right?
Yeah. And can we have, instead of the number 3 here, number 1 again?
Here?
Yeah.
No. This is the index of nodes. It is 0, 1, 2, and 3. It is like an array. You have index of your elements, which is starting from index 0. and they are unique. Yeah, so basically, there couldn't be a duplicate of nodes 1.
Oh, I got it. So it's indexes, it's not values.
Indexes, yes, it is not values. It is indexes of the nodes. Yeah, it's a great question. Yeah, and this one, yeah. So basically, once you will process 1 and 4, you will have this cloned function. You will return here, and it will return with all this relationship underneath. If yeah, someone wasn't clear. Yeah, so basically it is indexes. It can be that you will have. There is potentially could be a relationship between 3 and 1, means 3 has neighbor 2 and 1, but no. Yeah. Okay, cool. I'm glad that you're asking questions, folks. It makes clear for everyone. Okay, then if we finish here, again, if something is missing, just feel free to reach me in private message or ask on the Slack. System design, a link to the. Elia, I don't understand your questions. Did you find the link to? Do you ask the link to the whiteboard or?
Yes, sorry for that. Yeah.
No worries. Did you find it?
No, I don't. I'm still new. I don't know where to find things.
Yeah, it is on chat. Probably when you joined, you don't have the chat above. Yeah.
Okay, thanks.
Okay. Now, one of the popular one task, count islands. Oh, it's a very popular task. And actually, it's very easy one. Once you understand how to solve it, it's very easy. It's like, yeah. So the idea that you will have as an input matrix, I believe. Just, we'll double check here. No, well, yes. So basically, you will have representation of grid. The matrix representation of the graph. So, and you need to count islands. Islands represented as 1. And if there is 0, it means water. So you will have as input a representation of matrix, adjacent matrix. And you need to count the actual islands. On this example, we have 2. This the one, and this one the second one. An island is formed by connecting adjacent islands by 4 directions, which will be up, down, left, and right. And there is it can be one island because the connection between is actually the vertical one. Sometimes there is could be 6 directional or 8 directional. It will be when you encounter actually this one. Yes, it will be 8 directionally. Then yes, you have actually just one island. But in this case, because we have 4 directions, there is actually 2 islands. This one things will be also important to understand. This is related direction is related when we are speaking about, I don't remember that when it comes to adjacent list, there is no. So basically, when you have matrix representation of the graph, there is always will be either 4-directional traverse or 8-directional traverse defined as a part of description. I will explain how we're usually dealing with this, and it is very important to understand as a part of adjacent matrix. From the description point of view, is it clear? Okay. So we determine how to find all islands in the matrix. Let's consider input that contains only one island. There is this one island. What is interesting? So basically, you have this matrix as an input. Once you will extract it, you actually can see that it's that it is actually a graph. Because for me, it was confusing at the first time, like, okay, matrix, adjacent list, we have representation of graph, which is, should looks like this, or should looks like this, how it all matrix is mapping here. So that's how actually, once you will extract whatever definition implies to your relationship, so this is how this graph looks like. Is it, this is click, fix. So yeah, we have representation of matrix, but actually when we extracted it, it is a graph, which is a undirectional one here. Sometimes it could be directional one. In next week we will cover matrix with actually a directional graph inside of matrix. Okay. When we iterate through the matrix, starting from the top left, the first length cell that we encounter is cell. So yeah. To the key observation is that we should be able to access every length cell in the same island by moving horizontally or vertically through neighboring length cell. The same idea is similar to graph where each cell is not and adjacent list. So yeah, basically I just explained it by my words. What is written here? Once you will traverse matrix, in order to find at least first cell of relationship between ages, then you will need to find the whole island by traversing. So for example, you're starting from here, you know it's water, then you're starting from, then you traverse matrix back. It will be, maybe it's not clear now, but it will be clear once I will show code. So the idea is that you somehow start to traverse this matrix, right? Because from the initial input, you don't really know where is islands is placed. So you will start from first cell. You will move to the second. You will every time checking whether it is water or it is actually the earth. So once you will ending up finding that it is this cell is actually containing something, you will need to go from this cell and try to find if there is an actual island and what is the actual island. Because otherwise, if you will traverse this water, you encounter earth, but you don't know where is the island bounds. You need to traverse the whole things vertically and horizontally in order to actually find this island. Otherwise, imagine you just encounter cells. This one not count, this one not count, this earth, okay, we will start counting. This not count, okay. This one, again, we found earth, but we can't say, is it belong to the one island or it is already the separate one. The idea is that once you encounter in any place one, you should go and see where is this island's bounds actually, to traverse the whole these things. Is it clear here or not? It could be not clear. Okay. So for example, if there will be 0, meaning this one island and this one, we can't just go out of the cell and count the islands because there is one, there is no, there is could be it could be second, or it could be belong to one, or it could be the separate one. So yeah, once we encounter any earth, we should try and find if it is one island. That's how this task we are going to solve. Is it clear? Intuition behind, and why we can't just traverse along the cells? Okay, cool. In this case, we will use depth first search, but again, is you just traversing? VFS also could be applied, but the best version to solve this task is devise. For each cell we visit during the traverse, we need to mark that cell is visited to ensure it's not visited again. There are two, again, is it clear why we need also track the visited cells? Why we can't just, because, yeah, as I extracted here, it is graph, and it is undirected graph. You started from here, you go 1, you go 2, 1, and this one is actually connected with 1 and 1. Otherwise, we will keep looping between this all relationship if we are not going to track if it was visited. So treat the visited here is the base case for the recursion functions, which is will keep you from looping across the graph. So cell is visited, ensure is not visited again. There are two ways to do this. We can use a separated data structure, as we did in previous one. There was hash map where we were putting nodes. We used actually visited data structure for 2 papers. It was tracking visited nodes, and also it was returning the associated clone graph for us. Usually it can be just hash set where you're just putting nodes which you visited so far. It's meaning that you need to use a separate data structure. But in graph, what we usually doing, because this means when you're putting coordinates, visited cells in the separate data structure, you're actually consuming memory. But you can just modify matrix by changing the value of visited cell from 1 to -1, ensuring it doesn't get revisited. In this case, as we are working just with values 0 and 1, you can use any value here, and it's also input as a char. So basically, you can put like ABC for your visited, whatever you want, just to mark, make just not 0, or actually you can put 0 as well here. I used to implement it with 0. So basically, I just was marking them with 0, which is also will differentiate. So is it clear regarding this approach? How we are going to mark the nodes which is visited so far? Okay, this is very common approach for matrix as well. This is the example. So we will start from this node. We will right away mark as it visit. Next, we will go to this one. We will go, means from 1, we won't go here because we know that it was visited. Okay. Matrix with multi-island. We can identify all islands using the following steps. Okay. This was only one island so far here. But now let's look how we are going to find when how many actually, when there will be present more than one island. Just 1 second. Yeah. Can identify all islands using the following step. Upon encounter a land cell, explore its island using the first marking each island we encounter. Keep searching the matrix for any unvisited land cells. When we find one, repeat step 2 and 4. So how we usually, in this example, we have only one island, but we are asked that we can potentially have many islands on the matrix. How we will do this? So this is this one code, right? Yes, yeah. So this will be our main function, which is will be started here. Just 1 second, I will show you. This is our main function. And this one is main function, which is you need to implement in order to find all the islands. This is the input. You have as input your matrix here. This is a Python definition, I believe. In Java, it looks like this. Oops. Folks, correct me if I'm wrong, because I'm not very familiar with Python, if it's correct. So in Java, there is will be this way represented. This taking int actually in this case. In this case, we are working with chars, but the main algorithm will remain the same. So this is the base case. We just checking if matrix is not null. Then also adding some checks on the length. If it's 0, I also return 0. This is our output, because what we ask to count the islands. That's how we are traversing matrix. We're traversing row and column. This is probably will be unfamiliar for those who never deal with matrix itself. But this is this is how you usually traverse matrix. If there is any questions, meaning you will start from row, you will take row 0, and while you want and you will this indicates that the 4 started from row. We are here, will be starting, and there is every column until to end. We will going. So meaning here will be our 0. Here will be our 1, and here will be our 0 cell. Here will be 2, and here will be 3. This is the column, this is the row. Here we will start from the row 0, and we will go like this. 0, this was first cell, then will be second cell, then will be third cell, and then will be the fourth cell. Is it clear? Once we're done with a column on this row, we will go to next row. And next will be 1, 0, 1, 1, and 1, 2, and etc. Is it clear? Okay, cool. So row by row, we are going. Here's the cell. This is exactly what I did. This will be our matrix, which is 0 first, and here 0 second. This is the matrix. Then it will be 0, 1. That's where we're putting row and cell. So this basically, it is contain the value of the cell. And we're checking if the cell is 1. In this example, we will start from this. It is 0. It is 0. At this place, it will be 1. Once we will find the value, which is 1 in the cell, we will call our devise function. Devise function is the same, not the same. It's different from matrix implementation. Just keep aside. I will explain code here. So we will call devise on 1. all this will go, again, we will call the first function, which is recursion function. We will start calling all the one. I will explain what in the code of the first. And once we are done with traversing the first, we should go out of the first function at some point. And here we will, means we finish here, we encounter one island. Next, we will go again here. So for example, it was this cell, which is encounter 1. Means once we went out of this code, we will come back to the 0, 3, right? Whatever happens here in the first function, it doesn't change our walking through matrix logic. Meaning we will go here and we will encounter 0. But because we run the defs function here already, and here we modify our matrix. Once we will go to this cell 0, 1 over here, we will find -1, not 1, because once we execute the defs function on this matrix, we actually change the matrix value. And that's why we won't call this code again on this cell. But, for example, encounter this one example. We call the defs here, and we are proceeding with our walking through the matrix. We go to this cell after all. We go to this, and this. And now we encounter 1 again here on some cell. We will call our defs function here. We will mark all of them -1. We will modify our matrix. We will go out of the matrix and we will increase our count. At this moment, we will encounter 2 islands already. Is it clear how the main function is working? Okay, so the important things to understand that we are calling the defs, but it is not something which will change here. You will anyway go out of the cell. Doesn't matter if you will visit in the first function already these cells. It won't impact how you're going to walk through all the matrix here. So anyway, you will call. The one thing what it makes different, that next time when you will go to this cell, you already know that you visited it because it's -1, it's not 1. So now moving on to the implementation of the first function. We are putting here, we are sending cells from where we are starting. We're sending a row and column, and we're sending the representation of the matrix. We modify exactly the same matrix here. So this cell right away we're marking as -1. Now, as we need to explore matrix, and as we are elaborating on the not adjacent list, but we are working in the matrix here. So the difference is when you are working with adjacent matrix, how you're taking neighbors, you're taking from the list. But when it comes to the matrix, you need always introduce this directional array here. So let me just show. I usually prefer to keep it as a global variable, dir. While in this example, it is created here in the for. But I prefer to keep dir is somewhere here. So this is the one thing. So you are creating two-dimensional array. With this, you define it how to moving. This is probably also worth to explain. Just 1 second. I will explain this, how it works. So imagine we have this cell. We'll take this one cell. So it will 0, 1, 2, 0, 1, 2. The cell will be 2 and 2. Oops. Is it clear from where I took the dimension of the cell? Okay, cool. Now we need traverse this way, and this way, and this way. This is the neighbor of these cells. So we need to check this one, and this one, and this one, and this one. How it is work now? In order to find dimension of the next cell, we're using this formula here, which just makes, so meaning we take the direction of the next cell. It will be, first it will be a row. It will be our 2, because we have this R. This one, R and C. What we're doing here, next, we're taking direction, and we're taking -1 from here. So first we are executing for here. We took this one, meaning from the beginning we are working with this one, -1 and 0. Is it clear from where we took it? Okay. We're taking D pointed to the value -1. So it will be 2 -1. We will receive new NR, it means new row. It will be 1. And next, new column 2 here. We will take D1. It will be 0 plus 0 will be 2. So we will receive new cell, which is will be 1 and 2. This new cell, it will be pointed to this one neighbor. To this one neighbor. It will be 1 and 2. So that's why we will how we will check. Next, we will take this one dimensions, 1 and 0, and we will receive. Let's count what we will receive. Here will be 2 plus 1. It will be our 3, and here will be 2. So meaning we will receive this cell. It will be 3 and 2. Next, we will take this one, 0 and 1. It will R will be 2 and -1. Here will be a column 2 -1, which is will pointed as R still 2, but the column will be reduced by -1. It will be pointed to this cell, and the same for this one. So basically, why we're using this two-dimensional with -1, 0, and this one to make the calculation to find the neighbors of the cell on which we are now. Is it clear? This is the static one. It won't never change. So basically, it's used just to make this calculation in order to find neighbors of these cells. Please ask questions, Fox.
Yeah, thank you, Lilia. So when we have like the R plus D and the index 0, that's when we're like inside the matrix and we're running the depth first search for that particular cell.
Yes.
Yeah.
See.
Okay.
Yeah. First. Yeah. In the phase. So first we need. Yeah. It's the same. Like for JSON list. Yeah. When we were working here with the recursion function as well with the cloned one. Here we had list of neighbors, right? Because node we already had the list of neighbors. In matrix, each cell also has their neighbors. But in matrix, we find them a different way. But yes, we need to find these neighbors by using this formula and executing next devise here. So for example, we will call devise on this neighbor. And we will call once we will find devise on this neighbor. And we will also looking for devise on this neighbor. I mean, yeah, if I correctly understand your question, your question is once we find the neighbors, will we execute devise on them? Yes.
Yeah, and that's why it's the constant is it's static because it won't change because you're just checking the coordinates around that specific point, and then you move to the next point. Okay.
Yeah. So basically, once we will be here, so for example, this I will take this example. So we will execute the phase here, and we also will add some checks where we will decide whether we are going forward, because we know this is what probably we will call the phase on 0, but we won't go to count neighbors because we know this is 0. But this one earth, we will call the phase here. And again, we will use the same static two-dimensional map in order to find his neighbors. And why it is static? Because as you can see, we're using the same value to find row and column. So this is something which is you just folks need to remember. There is not from somewhere we're coming up during the interview. This is the fixed numbers. This is how we find the neighbors in 4 directionals. If there is will be 8 directions, there will be 4 more values, which will help you to find the neighbors from here, here, and here. Yeah, Ellie, please ask question.
Thank you.
Thank you. So my question, I have 2 questions. The first one is like this private static final one. Is it like something that has been given to us?
No, it's something which is you should know. You should remember by heart. You see matrix. You see graph in the representation of the matrix, and you should know how to traverse neighbors in the matrix. That's how it's something which is you should remember. This is 4 directions, but there is could be 8 directions.
Okay. And the second question, I was a bit confused. How did we use that to get the next neighbor? Do you mind just like, to explain that again?
Yeah, sure. So in this code, so I will remove this one probably for now. So you're just going in the for loop of this 2-dimensional array, meaning here you will have first -1 and 0. Then next iteration you will have 1 and 0. Next iteration you will have 0 and -1, and etc. On the first iteration, D0. D comes from here. I mean, it is comes from here. So here, D0, it means index. You have array of 2 elements here. So it is 2-dimensional array. You have the main array and where you're keeping the smallest array. So D0 actually pointed to -1 here at the first iteration. Then D1 will be pointed to 0. On the next iteration, you will work with this array. And first index will be pointed to 1 and second index will be pointed to 0. Is it clear, Ali? And
Yes.
it was your question.
Yes, thank you.
Okay, so basically, folks, one thing, if it's matrix, and from the description it's written 2-directional, this how you're going to find neighbors. You define it. You just it doesn't matter the order, by the way. You it could be different order. It could start from 0 and 1, 0 -1, or 1 to 0. In this case, it doesn't matter which is order you will traverse. Next, you're going from the loop, and you're creating a new dimensions for the next cell, for the neighbors. So basically, you're taking a row and column from here, from your initial cell, and now you just calculate another cell, which you want to check. Another cell, it's basically the neighbor. That's it. Okay. Next, we need to check if in order. So, for example, we found our neighbors here, as we discussed before. This will be our neighbors, and this one our neighbors, and this one. Next, we need to check if it's first check if the R is still in bound, not we're going out of bound, because here we don't check. It could be, so for example, for this cell, we will calculate this one cell, and this one cell, but also we will calculate this one. Nothing will stop us, because what we're doing, we just applied static numbers here, and we are not checking bounds. In order to not go, do not ending up with index out of bound here, we need to check if R is still in bounds, row and column is still in bounds. So this is basic check. If it's not going beyond of the 0, and if it's not going beyond of the size of your grid. Is it clear? Okay, cool. So this will be the first check. If it's a new cell is still in the matrix, and another cell and another check will be if it's earth. And it's not water, and it is not something which is we already visited. Because in this case, I'm putting 0, but in this explanation, we're putting -1. So in this case, we are not going to, meaning we are not going to execute here the first, here and here the first. We will execute the first only here. The same applies. So for example, if it will be still 1, we are not going to execute here the first, here and here and here, because we have our inbound logic. And once we will exhaust it, we are not returning anything here. We will just go out of this recursion function. Because it's void, it doesn't return anything. So basically, you're just walk through all the earths, you mark, you modify the grid, you went out, and then you just count the total and come back again to look of the cell if there is any other island is left to visit it. So yeah, I believe it's the same. Yeah, we're checking the same bounds. It doesn't return anything. Once we process matrix, we're going out, and then we just encounter count. Is it clear? Yeah, you will get used to it. Just try to practice. Just after the lessons, try to just to apply the knowledge which is discussed. So just to sum up, or any questions, because I'm going to sum up these two different tasks which we cover. Okay. So the difference you saw, we discussed the representation. After representation, we cover two tasks, which is actually cover two different representations. When we have a JSON list, it's for me it's more easier than with matrix. So you just using the list neighbors. That's how you're going to traverse them. When it comes to matrix, there is two things which you should remember. You're using directional dimensional array. It's 4 or 8 directional. Next, one, you're not using separate data structure when you're working with the matrix. It's almost always the case. You can modify matrix in place. So this is something which is, yeah, need to remember. So basically that's it for today, folks. Any questions? I hope it was useful and I didn't overwhelm you. Intentionally, I was thinking to include one more, but decided, okay. Okay. If no other questions, then let's finish half an hour or earlier to have our wonderful Saturday. Thank you, folks, for attending. Hope to see you next week. Next week will be also interesting. Welcome. Thank you so much.
Bye. Thank you.
Yeah.
Thank you. Bye.
Thank you. Bye.
Thank you so much, Lilia. Appreciate it. It's been great. Thank you so much. Bye.
Thank you. Bye. Thank you. Yes, please ask question number.
I was wondering if you could send HackerRun link again, please.
Yeah, sure. Amber, your first time, right? Join us.
Oh no, this is not the first time. I've joined multiple times.
Okay, cool. Okay. Otherwise, I will share this HackerRun link on Slack. But yeah, 1 second, I will share here as well.
Thank you.
You're welcome.